Good afternoon, everyone. I'm Chandrashekhar Choudhary, a PhD student working with Dr. Towley at the Department of Electrical and Computer Engineering at University of Cincinnati. Today, I'll present our work on a non-invasive calorimetric sensor for water flow event detection in premise plumbing systems. So the peak water demand estimation is of utmost importance when designing a premise plumbing system and for a new building, as it governs the size and cost of the entire water supply system. The traditional method for the estimation, called the Hunter's curve, was developed in 1940 and has become outdated with the broad adoption of water efficient fixtures. This leads to significantly overestimated peak water demand and thus oversized plumbing systems. Oversized plumbing systems can trigger potential problems such as higher construction cost, energy and water wastage due to inefficient water heating, and other health concerns like opportunistic pathogens like Legionella, and a new method to provide greatly improved estimate of peak water demand has been recently developed and adopted in the National Uniform Plumbing Code in the US. However, it requires a critical piece of missing information called the p-value or probability of the fixture used during peak hours for all fixture types in a specific type of building. So the estimation of p-values for various fixture types requires collection of extensive field data on percentage of time when a fixture is in use from large number of fixtures distributed in a target type of building. The data needed is essentially time-stamped binary on-off switching events, and flow rate information is not necessary. There are no solutions currently available with such capability. For an accompanying in an accompanying paper at this conference, we are reporting a solution based on a wireless sensor network using a cluster of miniature wireless sensor modules deployed at individual fixtures distributed in a building. The paper will be presented tomorrow at 2:30 p.m. in Sensor Networks and IoT session. I would like to invite you all to join us during that session. So the methods for water flow detection can be categorized into invasive and non-invasive. Invasive types, while low cost and widely available, require changes of existing plumbing by cutting the water pipes and inserting sensors in line with pipes, making it challenging and costly to deploy, particularly at large-scale deployment sites. Commercial non-invasive flow meters. Commercial non-invasive flow meter products are typically based on ultrasonic sensors, which are sophisticated, expensive, and not amenable to large-scale distributed sensing. Very limited work has been done using other non-invasive methods like microphones for agricultural and smart home applications, and calorimetric sensors for air conditioning applications. Key advantages of non-invasive sensors is that they are easy to deploy and do not require changes in existing plumbing, leading to significant cost savings. This makes non-invasive sensors the more suitable choice in our large-scale distributed network. As you will hear from tomorrow's talk, we incorporate microphone and calorimetric sensors in our sensor module for cross-checking and redundancy. So in this paper, we report a non-invasive calorimetric sensor implemented with low-cost components and optimized for deployment on water delivery pipes for binary detection of water flow on-off events. The principle of calorimetric flow detection is illustrated in this figure. Two temperature sensors are placed symmetrically beside a heating element on the pipe. One of the on the upstream is the T1, and on the downstream side is T2. When there is no flow, the both upstream and downstream sensors record the same temperature, which is when there is T1 equal to T2. When there is a flow, the temperature gradient is shifted downstream, causing a temperature difference of delta T, which is T1 minus T2, being greater than 0. This delta T can therefore be used for water flow detection. This concept of thermal flow sensor either invasive or non-invasive, has been has not been demonstrated has been demonstrated for microfluidic devices as well as air conditioning for HVAC systems, but has not been applied. So this is the design of our calorimetric flow sensor. It consists of a heater bridge, a printed circuit board, and a sensor mount. As shown in the cross-sectional view BB dash, the as shown in the cross-sectional view BB dash, the heater bridge follows the curvature of the water pipe with a protrusion in the center for integration of heater coil. The bridge has small width and is partly reduced thickness to minimize the heat loss along the bridge. As shown in view A from the side, miniature temperature sensors with high resolution of 0.005 degrees Celsius are symmetrically mounted on the PCB. The sensor mount includes guideposts and recesses for precision in sensor components to achieve symmetric placement of temperature sensors relative to the heater coil. The sensor mount also has a curved counter matching to the water pipe for easy deployment of the sensor. A thin layer of thermal conductive paste is applied on the heater coil and temperature sensors to improve heat conduction with the pipe. And so the thermal isolation between heater and temperature sensors to minimize direct heat transfer between them is essential for effective detection of water flow. The use of heater bridge and large opening in the PCB avoids direct contact between the heater and the PCB and minimizes undesired direct heat conduction paths. This significantly improves thermal isolation between the heater and temperature sensors, allowing better thermal coupling with the water flow inside the pipe to facilitate thermal flow detection. The sensing mechanism was simulated in COMSOL multiphysics. Laminar flow module was used to simplify simulation, even though the water flow in pipes is typically turbulent. A 1.5 watt point heater was used for simulation to model the effect of water flow on the temperature gradient caused by the heater. The simulation conditions are summarized in this table. This figure shows a typical simulation for the simulated temperature gradient in copper pipe with the presence of water flow, clearly showing the non-symmetric temperature gradient on two sides of the heater. The distance L between the heater and the temperature sensors is critical design parameter that affects the efficiency of thermal coupling with water through the water pipe. Simulations were performed for a series of L values to find the maximum delta T in presence of water flow, as the largest delta T indicates maximum thermal coupling between the heater and water through the pipe. The top figure shows the simulation model on a 3x4-inch copper pipe used for optimization. The bottom image plots the simulated delta T in blue dots at different L values. The optimal length of 12 millimeter was found, and this was compared with experimental optimization results discussed on a later slide. The circuit schematic for the device is shown here, including temperature sensors, a Raspberry Pi computer unit, and a heater driver. Commercial high-resolution, high-precision miniature temperature sensors with low cost are used. The Raspberry Pi is used to control the heater through the MOSFET-based heater driver. Furthermore, it records data from the temperature sensors over the I2C bus and processes the recorded data for water flow detection. Photos of an example device are shown here. The heater bridge and the sensor mount were both 3D printed from a Form Labs Form 3 high precision printer. High temperature resin was used to print both the parts. Insulated nichrome wire of 50 microns diameter was wound onto the heater bridge using a custom built machine to make the heater coil. The fully assembled device for deployment on a 3x4-inch copper pipe has a length of approximately 40 millimeters and inner diameter of 22 millimeters. All the experiments reported in this paper were performed on a 3 by 4 inch K-type US standard copper pipe connected to the city water supply line. A series of experiments were performed for the optimization of the distance L using the setup shown here, and that allows the L to be varied. The experimental results are plotted in the bottom figure in the orange dots, indicating an optimal L of 12 millimeters, which is consistent with the simulation results as shown in the blue dots. The symmetry of heat conduction from heater is important to minimize sensor offset. This was experimentally evaluated with the assembled device mounted on a copper pipe as shown here. The heater was turned on with the pipe filled with water but no water flow. The readings from both temperature sensors are plotted here. Both T1 and T2 readings show a consistent 1 degree increase after the heater was turned on. The delta T shown in brown color remained stable within a small range of 0.05 degrees Celsius, indicating excellent symmetry of heat conduction achieved by the symmetric design of the device structure and thermal isolation. The assembled device was deployed for water flow event detection using the setup shown here. The heater was turned on and the water flow was turned on and off repeatedly to emulate water usage events at a fixture. This figure shows the recorded T1 and T2 temperature readings in blue and green, and the calculated delta T in brown curve. These curves show clear pattern in following the water on-off cycles and successfully verifies the principle and functions of the calorimetric sensor, indicating effective device operation. A negligible delay up to of 3 seconds was observed and is not expected to affect this target application. So in conclusion, we have developed a low-cost sensor based on calorimetric mechanism for non-invasive detection of water flows inside water pipes with ease of implementation and deployment. The sensor has been successfully tested on copper pipes. The device is ready for integration in sensor module. The device is ready for integration in the sensor module for deployment in a wireless sensor network. Future work includes field tests of the sensor and exploration of other application scenarios. So our team members from the AIM lab at ECE Department of University of Cincinnati include myself, Professor Choudhary, and Gagan Batra. And we also have like Dr. Buchberger from the Department of Civil and Architectural Engineering and Construction Management. So I would like to thank our sponsors, NIST and the Ohio Water Resources.